All right. So in this video, we're going to take a look at normal distributions. So essentially, when you're dealing with a normal distribution, you know that the graph will look some sort of like a bell shape, right? So normal would imply that the graph of your distribution should look like some sort of bell. So when we're going to read problem 7, possibly problems 8 and 9, we're going to, in almost all those problems, we are definitely going to draw some picture. Now, parts A and B are accent for very similar things, but they have some key differences. The key difference, like for example, when you read part A and part B, is that in part A, it talks about individual value, X. So we have that when I scale the bell-shaped curve, it would be in terms of X for part A. Now, for reasons that I'll explain in a moment, the sample means we will denote them as X bar, right? So the bell shape, the normal distribution, we'll label it as X bar for part B. Okay, so for each problem, you can think of it as, okay, there's a part A and B, and it just depends on the scenarios, okay? Um, so I need two pictures, and I just need to know my cases. If you have the left, right, or between case, it kind of tells you what to do in the graphing calculator on how to enter your values. You have X that stands for data value, A and B would be also X values. The mean is mu, sigma versus sigma divided by square root of n. For the technology notes as well, I want to mention that we do second vars Normalcdf, right? So to quickly show that in the calculator, you hit the second command, followed by the vars command, and then you select Normalcdf, which is the second option under distribution, okay? And then we'll have to do a few things. All right, so here goes. For problem 7, it states that assume that females have pulse rates that are normally distributed with a mean of 73 beats per minute and a standard deviation of 12.5 beats per minute. Part A states if one adult female is randomly selected, find the probability that her pulse rate is less than 79 beats per minute. If 4 adult females are randomly selected, find the probability that they have a pulse rate with a mean less than 79 beats per minute. So part A and B sounds almost the same, but they're just a little different here. Part A is talking specifically about individual value, which means that when I draw that bell-shaped curve, again, I mentioned this earlier, you're going to label it in terms of X. One of the key things that tells us that I can label this strictly in terms of X is that it says that one adult female is randomly selected. So one implies individual. Okay, so for part A, you could begin your sketch. You draw a normal bell-shaped curve. So it looks something like this. Now, because I'm doing this on the iPad, the graph for some reason, when I try to like make my curves, it doesn't come out nice. Okay. Now, at the center of your distribution will be the mean. So the mean is 72. And you have a standard deviation of 12.5. Now, the value of X that we're looking at is going to be 79. So 79 is located to the right of 72, right? It's bigger than 72. So let's say somewhere here is 79. And it says that I have less than 79. So when I want to shade in that area or region on this bell-shaped curve, it should look like this region. Anything basically less than 79. So this is my left case. Okay. So how do I enter this into the calculator if I want to find the probability? Well, it's going to be normal CDF of, well, for left cases, if you look at this image, this picture gives you the idea. Well, the very first value that I need is basically negative infinity, essentially. And you can't use negative infinity in the calculator, so we just use a more smaller number. We say negative 9,999,99999. So it's basically a negative sign with 8 nines in front of behind it. So 1, 2, 3, 4, 5, 6, 7, 8, comma, the value of x, right? So x here was 79. Your mean was 72. So 79, comma, 72, comma, standard deviation, which is 12.5. So we can hit enter, wait, 12.5, close parentheses, hit enter. You could round your answer to 4 decimal places. You'll get 0.7123. And that'll be the solution to part A. To do part B is quite similar. In part B, you're drawing again another bell-shaped curve. But this time, we're not labeling in terms of x. We're labeling it in terms of x bar. How do I know that I'm labeling it in terms of x bar? It says that we're finding the probability that they, meaning that the 4 adult females that were randomly selected, that their pulse rate has a mean. So the key word was the mean part. Now you're looking at a sample mean. So we have x bar, but the rest of the problem now will somewhat stay the same. You have the mean is somewhere in the middle, is at the middle, right? The mean is still 72. The standard deviation is still 12.5. Your, instead of having x was equal to 79, now we have x bar is equal to 79. But 79 is located somewhere here again. With loss of generality, we highlight this region because this is a left case. And we now use the, for sample means, we use the Normalcdf command, but this time, the only difference now is that we take the standard deviation and we divide it by the square root of n. And this problem, n was equal to 4. Okay, so you want to write that out as well. So for part B, we have normal CDF of negative 9999999, followed by our sample mean, 79, followed by population mean of 72, followed by 12.5, divided by square root of 4. So how do I answer this in the calculator? I do second vars, normal CDF, negative, all these repeating nines, so it's 4 of them, 5, 6, 7, 8, that's good enough, comma, 79, comma, 72, oops, made a mistake, comma, 12.5, comma, oh, no comma. After you put the 12.5, you divide it by square root of 4. So you got to do second x squared, put the 4, move the right arrow key if you need to, and then close parentheses. If you do this correctly, you'll get 0.8686. There was a part C to this problem. The part C was just a follow-up as to why can I use the bell-shaped normal distribution for sample means, just like what I did for individual values, namely in terms of x, variable x. The reason why I can use the normal distribution is because of the central limit theorem. If you look at the scenario here, the original data for pulse rates of females was normally distributed. So regardless of their sample size, the sample means are going to be normally distributed as well. Now, if your sample size is bigger than 30 and you know nothing about the distribution of your data set, then you can still use the normal distribution, right? So the only time when you cannot use the normal distribution is when you don't know if the original data is normal. Basically, you don't know its distribution. And when your sample size is less than 30, when both of those things happen simultaneously, right? So that wasn't the case here. The original data was normal. That was the pulse rates. So the sample means are also normal. All right. So I'm going to pause this video and then I start up a new one for problem 8.